Thank you, Liang. Thank you so much for that generous introduction. It's very kind of you to invite me to Texas. And this is not my first trip. I came here in October 2014 at the invitation of Mike Young and spoke at BEG. So it's 12 years later. You know, I mean, it's awesome to be here. And so the title of my talk is Progress and Challenges in Hydrology. Oh, I got it. But really, let's start off with something more important. Let's talk about the problems with your quarterback. You know, your quarterback has some problems. You know this, right? Ashman, I'll tell you the problem. I'm a big student of football. So, OC should move the pocket. You can't have a stationary pocket. You know, stationarity is dead in hydrology. You know, all of you guys know hydrology. You can't have a stationary pocket. Manning should change his launch point and angle. You know, launch point is everything. You know, big defensive linemen know how to jump. Old days are gone. They can jump and they can bat the ball down or even deflect the ball. 1 out of every 6 passes should be greater than 40 yards. You don't take a gamble, forget it. Hey, in baseball, every person tries to hit a home run. Come on, you got to throw 40-yard passes. And then lastly, don't scramble. In the NFL, DBs are 250 pounds, they run 4.4. Half M times V squared. You know how much kinetic energy that is. Actually, I'm just kidding. The quarterback is fine. So, I need to stick to my day job, which is hydrology. And this is hydrology, okay. So, the problem with hydrology is that land surface is heterogeneous. No matter how smart your model is, how smart your computer is, land surface is heterogeneous, which means soils, vegetation, topography. Very, very difficult to model. And hydrological variables are sparsely, if in situ measurements occur, and have long data records. So if you think about hydrology, what do you want? You need precipitation, air temperature, ET, soil moisture, stream flow, groundwater, all kinds of things. Very difficult. It's in US we are spoiled because we have lots of sites, we have lots of measurements, etc. Earth observations are much better. By Earth observations, I mean satellite remote sensing. For most time, I will stick to satellite remote sensing, though we can do other kinds of remote sensing. As the talk goes on, I'll show some of it. Earth observations cover much larger areas in space, but they're average. So Earth observation at a 1 kilometer resolution is an average over 1 kilometer. It's not a point. So you have to realize that. And second of all, that they are temporally sparse. So you can have satellites going around in polar orbits. Most of our satellites go in polar orbits. There are some sensors which are in geostationary orbits, but very few which we use, and they lack long data records. That's a big, big problem. And currently, the 3 big things at NASA, 3 big ones, GPM, precipitation, MODIS, and Aquaterra, and SMAP, are all going to end their lives soon. I mean, it's not a question of if, it will be a question of when. After that, we don't have a continuity. And that's actually the topic of my front page newsletter for February in AGU Hydrology. Models have representations of physics, but they may be approximate. So, what do we do? What I tried to do a couple of years ago is try to formulate 4 challenges. And everybody has their own version of challenges. Everybody may have their own challenges in their area of research. But my 4 challenges were pretty straightforward. Do Earth observations compare well with in situ counterparts? Because I have apples versus oranges. And again, you know, somebody said, they used to use the word ground truth for observations in the ground. I am reminded of Jack Nicholson's line in A Few Good Men. Now, most of you guys are so young, you may not have seen that movie. You know, there is no truth. You can't handle the truth. There's no truth. And again, I don't know how to speak like Jack Nicholson, but you can't handle the truth. So we're comparing apples and oranges. Let's be very careful. When we compare them, we are not going to get an exact match, nor do we desire to do so. Second question, how important is precipitation in hydrological modeling? Because everything revolves around precipitation. Very, very important. Let's see how important it is. And can we get higher spatial resolution of Earth observations? Because having soil moisture at 9 kilometers does not do us any good. How do you define to your neighbor what a 9-kilometer pixel is? They won't understand it, and they shouldn't, because it's not very relevant. And then, how do we study ungauged and poorly gauged watersheds? So these are 4 challenges which I came up with. And what I'm going to do is piece together part of my journey in research and try to answer these questions. Earth observations. Now, Earth observations are very, very well set these days. And this is a decadal survey which was done in 2017, which tried to answer different questions, and it's all available. And now the National Academies is getting ready for this next decadal survey, which is going to come around soon. We're in a very good age of observations. We got all these hydrological variables from different sensors. These are all well-established sensors. Landsat does vegetation, land use, land cover, vegetation index, and surface temperature is also done by AVHRR. Some wetness and rainfall by SIMR and SSMI. Then you have a whole host of satellites for soil moisture, a whole host of them, and there's no dearth of it. And then obviously rainfall, trim, and GPM. And total water or water level are GRACE and SWOT. SWOT's a big thing now if you want to look at levels of water in lakes and rivers and in ocean, of course. And then you have atmospheric profiling. And if you throw all of that into a nice cartoon, this is how it looks like. So you have the hydrological cycle, both the atmospheric component and the terrestrial component, and each of those components has variables. And each of the variables are either directly, but most of the time indirectly estimated from sensors from space. Most of the times are indirect. But the problem is, most of these sensors go overpass at different times, and some of them have stopped working. So, there's a whole bunch of things which happen. So you can't really say that, I can just use observations and I'm done. It's difficult. You have to use it along with models. And if you put this into a nice movie, which was done by one of my former students, if you look at the rainfall, the soil moisture, vegetation index, and the total water, you can see as the precipitation moves up and down the ITCC, given by the GPM I merge, and the normalized difference vegetation index, especially over the continent of Africa, shows the vegetation moving up and down. And then in response to the rainfall, the liquid water thickness increases, especially in Africa. Of course, it does increase and change also in South America. And then the soil moisture shows the same covariability at the vegetation index, and especially in Africa. So you can do this and be happy that four different indices or four different variables derived from completely different sensors with completely different algorithms somehow match up reasonably well, at least qualitatively. Now comes to why we want to do this work. Because most of the time, there is an attack on the word climate. You don't have to use the word climate. You can use the word hydrological extremes. Even though this says weather and climate, I could use the word hydrological extremes, and I'll prove it to you. So if you look at this, and this is the LA fires of last year, then we have droughts, we have all. Each of these is $1 billion. You can call it anything you want. If you invest 1 billion, you'll be saving about 25 of it. You can count how many there are, maybe 25 or 30 of them. So the point is investment in sensors, investment in models, and above all, investment in science has a lot of ROI. And that's the most important aspect. Now, this has also been put into a table assembled into a table by one of my graduate students, and you can see the billions, they go all kinds of numbers. And it's like, I think this is very approximate. And this damages does not cover human life. We can't put a number on that. So remember, this is all property life, property. So everybody talks about climate change, and in hydrology, I have dabbled a little bit with climate change, but my definition of climate change is a little different. It's like, how does extreme events change? And are these extremes shifting precipitation? I've been very interested in precipitation. One of the things which we did was a very simple index. This was published, I think, 2 years ago in GRL. If you take for any box, this is gridded observations from Europe. It's called EOBS. It's publicly available data. If you take any box, you have daily precipitation for many, many years. And in this case, it's from 1950 to 2021. If you take those precipitation and every year and arrange it from biggest to smallest and stop counting the number of days when you reach 50%, it's called WD50. That is the number of events or day events where you get 50% of rainfall. And you can see, if you compare between 1950 and 1985 and 1986 and 2021, in this latter 35-year period, the box is filling faster. That is, there are a bigger number of larger rainfall events. And that's not good. It's like asking you to eat a week worth of meals, 21 meals, in 10 meals. I'm sure we can do 21 in 20. We can do 21 probably even in 15. But if I give you 10 meals and say this is it, there are people who prescribe to certain diets, but I certainly can't do that because it will result in lots of problems, because you have to eat all that amount of food, double the amount of food in that time. So same thing with the earth, the land surface. Because of these extreme rainfalls, you have a lot of other things like flooding, and more than that, landslides, soil erosion, debris flow after fires, etc. Huge amount of problems. Now, we move this to global, and this is the one with published last year, sorry. And you do the same thing, but in this, we are not using gridded point gauge observations, but we're using all the data comes from GPM iMerge. And you can see very easily what happens. That is, the latter half of that period, 2012 to 2023, is lower than the previous half. So it's faster and faster filling up the bucket. Okay. And this is a hydrologist's simple answer at climate change. So when I go and talk, now I don't use the word climate, I use the word hydrological extremes. And hydrological extremes in my definitions are floods, are droughts, are landslides, are permafrost thaw, and wildfires. Basically, what is happening is each of these is somehow linked with water. Too much of water, too little of water, thawing of water, water in the wrong place at the wrong time, resulting in slope instability, and of course, too little of water followed by, ignition. So we have a problem. We really do have a problem. So let's see how much of this we can answer with our, challenges. Do Earth observation compare well with in situ counterparts? And, there's a ton of publications. I would say easily there are 1,000 good publications on this topic, and covering all the variables I showed you in the first cartoon. So there is no dearth of it. But I'm going to just focus on one thing. And again, I'm focusing on the things which I did. So this is precipitation. So in a study over the lower Mekong River Basin, one of my former students, Chelsea, studied, this is how the lower Mekong River Basin looks like. And if you know anything about the Mekong, it's flat as a tabletop when you get down to the Vietnam Mekong Delta. But up in the hills, there is some topography. And the rain gauges exist more in the flat area than in the mountain. Whereas we all know that the rainfall on the mountain makes the most difference for everything. So we looked at comparison between different seasons between TRIM precipitation, which is from the sensors, Earth observations, CHIRPS, which is amalgamated satellite sensor plus modulated by station rainfall, etc., and then compare it to in situ. And again, as I said, we are not going to get exactly same results, but they look kind of similar if you look at this. And again, for students who are more interested, all of these are published articles, so you can see it. But you can see that the two different sensors, the TMPA and CHIRPS, reasonably agree with each other, and they have a kind of similar agreement with the in-situ sensors. Again, in-situ sensors are dots, but this dot is very big. Really the dot should have been 1/100th of this. And then we also did a nice time series to see how it looks like. This is averaged over the whole basin, so obviously averages are easier to compare, and you can see that the CHIRPS and the TRIM reasonably agree with each other, and so at times one of them is off from the other, and you can see that they all show seasonal variability, and that's very important. It's something which we see. And again, you may ask, why did you stop at 2015? I think the Mekong Research River Commission, MRC, gave us only data for that time, so it could be easily extended to 2025. Now, we did the same thing for India too. India has gridded rainfall. I don't think they give you station rainfall. The IMD gives you gridded rainfall, and they have gridded rainfall for 100 years or something. It's something atrociously long. Of course, we only had 20 years, but we compared it, and we compared it for an average for 15 years, and the paper has more seasons and everything. But this is annual average precipitation during the TRIM period, about 20 years in India. And you can see, some things are off, absolutely, but we tried to put this not as a gridded product, but as a watershed boundary product. So each of them are in different watersheds: Indus, Ganga, Krishna, Pennar, etc., Kaveri, etc. So you can see that there is some resemblance, but there's also some differences, which we should expect. Okay. So that's the first challenge. So what's the second challenge? The second challenge is, how important is precipitation? There's a lot of papers on this, so don't take my word for it. You can just Google this out. Or now I should stop using the word Google it out as a chat GPT. So even for small catchments, precipitation is seldom spatially uniform. So it could be raining on your side of the street, but your friend living on the other side may not get any rainfall. It's very common. And occasionally we see that when we are driving on the interstate and there's a rainfall, and then 2 minutes later there's no rainfall. And then you go back into rainfall. So these rainfalls are cells, like a couple of miles in diameter. So it's very important to know that rainfall is never spatially homogeneous. So we did a study in the country of Vietnam. Vietnam is a very long country, and it has a lot of topography. For people who have visited, probably know it. So we took a few of these watersheds in this thing, and these watersheds are really small. I mean, it's so small that most of you could probably hike around it. Maybe it takes a few days, but you can hike around it. It's not. Some of them are really, really small. Okay. And then what we did was we tried to compare for these watersheds the rainfall from different sensors, and we took at the average, and this one is the runoff. This is the runoff generated by each rainfall input into a hydrologic model at the basin outlet for all these watersheds. Okay, but the more important thing is we wanted to compare these sensors. What we did is we compared these sensors for the stream flow derived at the outlet, pushing this rainfall into the model, and compared it with the P-bias, and the first one is the Nash-Sutcliffe efficiency, and second is the percentage bias. So Nash-Sutcliffe efficiency very high is is good, and P-bias very low or close to zero is good. And all of this put aside, and I don't know if we did the rain gauge for the P-bias, but what we observed was the GPM IMERGE showed the best results. And then we did an even more harsh test. In this, we used an off-the-shelf hydrological model called SWAT, Soil Water Assessment Tool. And we used half of the period to calibrate the model. The top panel shows calibration using the rain gauge. And everybody knows how to calibrate a rainfall runoff model. And the second one, we use the rainfall and the parameters we calibrated to capture the stream flow. And this is at a very small river basin, the XL River Basin, in the northwest part of Vietnam. The second one, we did again half calibration, half validation, and the calibration we did using the data from Earth observations. And the second part, we used the calibrated parameters and ran it through the model. What's very exciting to see about this is that the calibration part for both the rain gauge and the Earth observations are reasonably similar. One could argue that 2.9% is closer to zero than minus 9.6%, but it's reasonably similar. But where it hurts the most is that when you have calibration using rainfall, which is erroneous spatially, then what happens is that the parameters don't translate into honest numbers. And when you run it, in the second part, you don't match these high values. And for hydrologists, high values of flow are very important, because that's the part where you have a flood or you need to empty a reservoir to make sure you have space to store the incoming water. So you can see over here that a simple thing like calibration of a model and then trying to understand how it works out, makes a big difference when you use a spatially distributed rainfall input, ergo Earth observations. Third challenge. And this is a challenge which I spend a little bit more time on because it's how I started my whole career on remote sensing of soil moisture. Can we get higher spatial resolution of Earth observations? As I said, if you show somebody a 9-kilometer soil moisture, nobody's going to get excited. I mean, everybody wants now 1 kilometer, 400 meters, 30 meters. Some people talk about meter scale stuff. People are all interested in high resolution. Okay? So what we did is many of the Earth observations are limited in spatial resolution due to technology. For example, very simply put, microwave remote sensing is all about antenna size. If you don't have a big size of antenna, you cannot have a high spatial resolution because it's a very simple high school physics-based problem called Fresnel's law of diffraction. So if you know Fresnel's law, you know that the delta x over d, the diameter of the antenna, is delta x over h. H is the height between the sensor and the ground. Delta x over h is lambda over d. And you can derive this using Fresnel's law. So we can't have a 10-kilometer antenna in space. Impossible. Too heavy, don't have enough fuel, etc. So then what we did was we used a very simple principle for soil moisture called thermal inertia. It's very simple. If you have very low soil moisture, like in a desert, the day-night surface temperature difference is very high. For people who have gone camping, you will realize 2 a.m. is a lot cooler than 2 p.m. Huge cooler. Now, on the other hand, if you have gone to Corpus Christi into the water, the temperature difference between morning and night of the water is probably 2 degrees at the most. So water is a big modulator because of evapotranspiration or evaporation. And this slope gets less sensitive because of vegetation. Vegetation has a shielding effect as well as an evapotranspiration effect. As a result, that slope goes a little down. So you can see that using this and using 30 years of data to generate that lookup curve, which I just showed you, we can get 1 kilometer soil moisture and then normalize it all down to the pixel size, the original pixel size. So you take the original pixel, the original map of soil moisture, and use this simple principle to just break it up, distribute it. Very simple, unbiased distribution. So the average of all the small pixels is equal to the large pixel. Very, very simple. And we did this, and we produced a lot of data. This is a 1 kilometer global soil moisture product published in Vedozone Journal, as well as available online. And I'll show you where it is online. So you can see over here that when you go down to So when you go down to 1 kilometer at the global scale, it is much more difficult to see how good the resolution is. So I'll go down to a catchment to show you that. And then we also did this for 400 meters, in which we use a different sensor, but at a 400 meter scale, to get you global 400 meter soil moisture. This is 400 meters, and you can imagine that that's a very high resolution, but we have also validated it, which I will show you. I don't want you to just believe me. So one of the things people always get upset about is saying that, oh, how much data do we have? How much data do we have? Because we are using temperature. So in parts of the world which is covered by clouds, you will have less amount of observation. So if you look at this, you can see over here the percentage. This is the data availability in percentages. So the times in at the 9 kilometer, you have a high value because you are not using any thermal data to downscale. This is the original product. But when you get down to 1 kilometer, you're looking at 30%, 20 to 30%. But when you get down to 400 meters, it's even lower. How does it affect us? Not really. So it's instantaneous numbers. So we give out the 400 meter data or 400 meter observations every instant it is available. It's not averaged. And you can do whatever you want. You can average it over a month, over a year, whatever you want. But it's instantaneous numbers. It's slow because of clouds. Okay? But you do get a very high definition. And how high is the definition? So you can see over here, this is an example of the 1 and the 9 kilometer for the Sacramento, San Jose, and the Danube River basins. And you can start seeing that it is so much finer than what you can see with the, if you see the 1 kilometer, which is on the top, and the 9 kilometer, which is the second row, you can see that this is so much more pixelated than the 9 kilometer. And it's very, very important because there's a lot of studies you can do, and one of them we talk about is wildfire potential. And wildfire potential is greatly improved by understanding the soil moisture. And this is, for example, for people who are interested in climate, especially US climate. This is the 8-day soil moisture using 9 kilometer, 1 kilometer, and 400 meter soil moisture. And you can see this is from 2 back-to-back periods, August 1 to 8 and August 9 to 16 in 2019. And you can see how much nicer or how much more pixelated, because within a week you can actually fill in all the holes, because you have some missing data, but within a week everything gets filled in. And you can construct a climatology, whether you want to figure out changes in the boundary layer or changes in flash drought propagation potential, etc. And there's a lot of studies on flash drought done using this data set too. Now, if you go down to smaller watershed, this is San Pedro, very small watershed. And look at this. This is very simple. It is June 18th or June 16th. I can't read it. You can read it better than me. June 18th, June 21, and June 26th. Look at that dry down. That's the 9 kilometer showing the dry down. It's just drying down. This is the 1 kilometer showing the dry down. This is the 400 meter showing the dry down. Now imagine you are a biogeochemist who is looking at the movement of nutrients or contaminants. Having the high spatial resolution soil moisture tells you how water will move and how this nutrient or contaminant will be carried. And again, I would agree with people if they say 400 meters is pretty low resolution. You need 30 meters or you need 10 meters. But this is a very good start. It's going down to the level of a field. And then, as I said, we are not going to tell you, take my word for it. All of these downscale soil moisture at the 1 kilometer and the 400 meter is validated using a global system of data sets. It's about 1,600 locations in the world. And one of them is right here. It was started by Michael Young from BEG, Texas. We use it a lot. So, if you look at this and you put all these data sets, and again, everything, all of the statistics is published in these manuscripts online. And you can see over here, this is Texas. And then it shows you the difference between the 9 kilometer, the original data set, the 1 kilometer, and the 400 meters. In most of them, not all, most of them, the 400 meter does the best, which says that if you go down to a higher spatial resolution, you get a better match with the in situ soil moisture, which makes sense, right? The in situ is just a point. And we do this for both the unbiased root mean square error as well as the spatial standard deviation for the networks. Most of these networks are not one site, but just like you saw in the previous picture, it's a bunch of sites. This is all hard work. I know Michael and I think his former associate, Todd Caldwell, work days and nights getting this data together. It's a lot of work, and it's all very expensive because, you have to set the sites up, and then you have to make sure they're maintained. It's not like you set it up and it'll do things good forever. You have to go to maintain it. So these are huge things, and this is the part where the spatial standard deviation, which is the spread of the data sets in this intensely monitored areas from in situ, is it captured by the 400 meter, the 1 kilometer, or the 9 kilometer data? And you can see over here, for most of the times, the in situ has the most spatial standard deviation. But the 400 meter gets close to it. Not complete agreement, but gets close to it, which is very, very important when people start talking about distributed hydrology. Now, all of this data is free and available. The 1 kilometer data is hosted by the National Snow and Ice Data Center, NSIDC, and the 400 meter data is hosted by us. I think we should move it also to NSIDC, but any data you want, this is all free. I would only want your MasterCard numbers. American Express not accepted. But seriously, this is the data which is provided, which is generated to be used by the community. There's no point in locking this up. So please use it. You can use it for any small catchment. You can use it global, whatever you want. And we'll be happy to work and help. Now, I said that I'm also going to talk about one more thing. There are Earth observations which are not satellites. The big advancement is coming in the area of UAV. So we have one of these, an L-band radiometer. It looks like this. It's I always joke, this costs more than my car, but it's a very expensive one. And this is how it looks. Let me see if we can make this work. So this is how it takes off. So it takes off. It's an air gun, takes off. And this is how it lands. The only problem is its landing. It belly lands. And as a result, it's broken 4 times. And for a $150,000 instrument, breaking it so many times is not a good idea. So we're going to switch to quadcopters, which are slower moving. This moves very fast, but quadcopters will move slower moving. But we can get 4 quadcopters for the cost of one of these. So, hopefully we can do it. But this is very good. But what does it do? What does it do? And we published this too. 5 meter soil moisture. And again, this is, I call it remote sensing on demand. So suppose you have a big rainfall and you want to know if there's going to be a landslide, just fly this thing over the hillside. And this is line of sight. So this is not something which you sit in your pajamas at home and fly it over, a watershed in northern Texas, 100 miles away. No, you can't do that. You have to be line of sight. And also these things are regulated by FAA to a great deal. You need a pilot's license, you need all kinds of stuff. And you can't just fly it anywhere because it is not considered the right thing to do. You have to get permissions. But when you get it and you do it, look at this. I mean, look at that, we did one morning and afternoon. You can see, the amount of increase in the dry down, morning to afternoon. See, this is the wet spot, no wet spot. See here, look at that. There's some parts which dried out much more. And, we did huge bunch of this. And then these things over here, and the paper has much more details. They show the actual soil moisture at every, about 20 or 30 sites along two lines, And so, this is something which we are very proud of because I think this is the future. This is what we can do in the future. Okay. So, the last question or the last challenge is, how do we work with poorly gauged watersheds? Because lots of places in the world, you cannot get the stream flow in the watershed, or it may not be of good quality. So even if you got it, it's not worth it. So what do you do? So this is where we made a foray into AI/ML. So using AI/ML models trained in data-rich regions, we can simulate stream flow in data-poor regions with better accuracy than when using the concept of hydrological similarity. And I'll get into the details of this in a second. So if you look at this, these three locations in blue are the training areas. S1 is North America, S2 is South America, S3 is Europe. These are really good because not only are they good, they're also good because remember, AI/ML cannot do anything without observations. In the blue regions, we have a stream gauge about every 11,000 square kilometers of catchment. In the red region, which is the test basin, it's South Africa and Central Asia, and you can choose more watersheds if you want. You have one stream gauge in 90,000 square kilometers, almost 8 times worse. So you can imagine that the density of stream gauges plays a big role in training a hydrological model. So we used this, and we used the following attributes for your AI/ML model, because all of the models need attributes. And these are the attributes for the static values, and you can get this globally, you don't have to work hard. And then the second one is the dynamic variables, because you don't need dynamic variables, the air temperature and the precipitation. Without that, you don't do hydrology. That's what all you need in most off-the-shelf models anyway. So we have 16 of these variables, and then we use some index, the metrics, to evaluate it. And these are simple correlation coefficient, Kling-Gupta efficiency, mean deviation, yada, yada, yada. Okay? And then we introduce this concept. This is very important concept. Hydrologic similarity. Most people think AI can do things everywhere. They put 1 billion observations in a box and everything comes out with R squared of 0.99. No, that's not the right way to do it. What we did was look at the L2 norm between the domain, the source and the target. Source is the blue, target is the red. And this is the L2 norm. And the L2 norm is for both the static and the dynamic variables most of the times together, all 16. Okay? It's an L2 norm. It's very simple. If the L2 norm is small, that means the two basins are hydrologically similar, because we have put all the static variables we can, and the only dynamic variables are air temperature and precipitation. You could put humidity, wind speed, other things, but radiation, etc. But we're going to a simpler one. Okay? It's very simple. So we would expect if the D2 is small, then you have similar catchments, and a model trained in the source catchment can be applied with reasonable hydrological confidence to a target. Okay, this is the result. The first one is output from a global model run at NASA. It's GLDAS. And so we pulled out this grid and saw what the stream flow was for Afghanistan. This is a catchment in Afghanistan, which doesn't have very good monitoring. Okay. The second one is a LSTM trained between S2 and S3. S2 is South America, S3 is Europe, and applied to Afghanistan. And the third one is a LSTM trained just in North America and applied to Afghanistan. And look at the radar plots on the right. If this all fills up to 1, then it is very good. The octagon is full. You can see that S2, S3 trained LSTM applies best to Afghanistan. And we've done a whole bunch of more examples, but for the sake of time, I'm only giving one. Then we went back and said, why did it do well? There's a reason why it did well. What we found is if the L2 norm is small, then the total number of experiments, and this is not one single experiment, this is the ensemble of all the experiments we did, in which the LSTM does better than the physical model, and at least 5 metrics are positive. At least 5 metrics are positive of the 8 metrics. The slope is a nice downward slope for just the static variables D2 and the static and dynamic variables D2. D2 you can calculate source minus target, you can calculate either for static or dynamic or both. So there is a reason for the good answer. It's not like I put a billion numbers and I got R squared as 0.99. But it's because the catchments are similar. And we did this on numerous catchments. So, how do we pull this all together? And we've done this over and over again for many, many catchments all over the world. But this one was one of the first ones done in 2018. If you look at the Mekong River Basin, this is all the way from China, all the way to the Gulf of Thailand, through the Mekong Delta. Very, very exciting place where we've done lots of studies. If you look, very simple, this is such a simple thing, you could do this in a term paper over a weekend. Nowadays, you can get this codes written even faster than what we did. If you look at the precipitation anomalies, dry month, wet month, and then look at the associated runoff anomaly from that model, GLDAS, compare it to the evapotranspiration derived from MODIS anomaly, and the Grace water equivalent thickness, more water or less water. You can see when it is dry, it translates to less runoff 2 months later, less ET 2 months later, and less water 4 months later. And same thing for the wet. And the beauty of this 4 pictures is that all of them come from completely different sources. No calibration, no model, nothing. It's just raw data. And then we did the same thing, but for a different basin. This is the Murray-Darling Basin in Australia. Same thing. Dry and wet. This one is even better. The dry and the wet months are a few months apart. August 2009 and January 2010. You can see dry anomaly, wet anomaly of rainfall. Same thing for runoff, ET, water equivalent thickness. So there is a logic that these things get translated, and Earth observations, not in an instantaneous, this is monthly numbers now, okay? They have some relationship. They're telling us stories of the system. And then, if you go to 2 different basins, which are a world apart. One is Amazon The other is Murray-Darling. Amazon, very popular for people who do hiking, outdoor camping, etc., or want to wrestle with an anaconda or some big python or snake or whatever. Murray-Darling is a managed river basin, very managed. They grow a lot of food, they grow a lot of animals, and now they're even growing grapes, all kinds of stuff. It's very managed, very, everything is cookie cutter. And then if I define a very simple anomaly index, monthly rainfall anomaly index, you take the monthly rainfall anomaly, like the one I showed you, and divide it by the climate for that month. This is a signal for the Amazon, which means it is very close to the average. Means every month, every January from 2000 to 2015 or 18 or whenever this goes up to 2019, every month of January is similar to each other. Every month is similar to each other. But on the other hand, Murray-Darling looks like this. And these are unitless, so you can compare them. You're not comparing the raw rainfall, you're comparing the rainfall anomaly divided by the climatology. So you're dividing rainfall divided by rainfall, it's unitless. So you can see the heartbeat of a system, of any hydrological system or ecological system, is precipitation. And Amazon is a much more resilient and stable system. I wouldn't even call resilient, stable system, Murray-Darling. I always joke when I show this slide, said I can still run 100 meters. I can. Probably 25 seconds now, gone from the low of a 13. But after I run the 100 meters, that's how my heartbeat will look like. I've heard that Usain Bolt has put on some weight, but I'm sure he can run 100 meters. But that would be his heartbeat. Because, it's the preparation of a system and the stability of the system which defines it, and everything starts in hydrology with rainfall. So then you can say, okay, we did all this stuff. Where is it important? This is the country of Chile. We had a great publication in this a couple of years ago. This is the antecedent soil moisture, and these are the areas, those polygons are the areas where fires happen. And decrease in moisture leads to fire. This is how it looks like. So the places where the fires happened, the burnt orange, and again, this was done by Benjamin Goffin 3 years ago, so we did not know I was going to give a seminar in Texas, who loves the burnt orange. But you can see low soil moistures, large low soil moistures leads to fires. Very, very important. So, to wrap it up, evolution of hydrological models using Earth sensors have come a long way. I started my work in grad school in the 1990s. And, we have 35 years and we have some answers, not all answers, but some answers. And when we think about AI, ML, 10 years ago, nobody knew anything. In 2 years, things will even change more. We all know that. So, we have to be patient. And being patient is a virtue. It's good to be patient because I think the best results of AI, ML are yet to come. Because the methods are not yet. And again, it's the logic. I think if we set the right logic, we'll get the right answers. Because AI, ML is changing. We can use that and harness it to our science. And the role of in situ observations cannot be downplayed. I don't care how much AI, ML you do, but if you give the policymakers the wrong idea, saying that you can do everything with AI, ML, they may say, oh, we don't need to have a seismological network. Oh, we don't need to have soil moisture network. You do AI, ML. They have to understand AI, ML depends on observations. And current observations, because remember, you can only do good with your model how you train it. If you don't have the extremes in your data set, you're never going to simulate those extremes. So it's very important for us to have more and more of these sensors, maybe smarter sensors, wireless sensors, etc. This is the people who did all the work. I didn't do anything. So these are the people who did all the work. Nice group picture at AGU. I'm sure many of you were there. I'd like to end with a quote from Robert Goddard, after whom the Goddard Space Flight Center is named. It's difficult to imagine what's impossible because the dreams of yesterday are the hopes of today and realities of tomorrow. Thank you very much.